So this is Exploring the Solar System. It happens to be part of a series, and this particular part is about the origin of the solar system. So it overlaps to a little extent with what I've said before about how stars come to be. So we can ask the question, how did our solar system form? What clues we have about how it came to be? And again, we can ask, what do simulations tell us about what happened billions of years ago? And I'll also ask what questions remain regarding the origins of our solar system. If we look at a model of the solar system shown here, this brass orrery, a model like this is built from the inside out. You start with the sun and then you add Mercury, Venus, Earth, Mars, etc. Well, that's fine for an orrery, but that's not how the solar system formed. As I said before, we know that star clouds, in other words, big molecular clouds, mainly of hydrogen, can collapse and form stars. When we look out into our Milky Way, we see this cloud 400 light years away. It's called the Rho-Ophiuchi cloud because it's surrounding a star which is called Rho-Ophiuchi. It's the nearest star-forming region to our solar system. And you can see from the scale there, it's many, many light years in size, as well as being a few hundred light years away from us. Hundreds of new stars are forming, and the total mass of a cloud like this is enough to make thousands of solar systems. And we believe that our sun and all of its attendant planets were formed in a hydrogen cloud similar to that one shown there. So a rough idea of the timeline, I'm trying to get everything on the same timeline so it all makes sense. The collapse of the cloud will take a few million years, and it will take a few million years before all of the gas and the dust that's surrounding a star after the star has been formed, for that gas and dust to start to be cleared. After many tens of millions of years, the temperature at the core of the star will be hot enough for hydrogen to start fusing into helium. That's what we call the start of the main sequence. And after hundreds of millions of years, all of the stars that are born out of that large cloud of hydrogen will eventually start drifting apart. So the early stages is basically a hydrogen cloud. After perhaps a few million years, that's where the sun is, remember, on this diagram of luminosity on the vertical scale and surface temperature on the horizontal scale. It'll take about 30 million years after the collapse of this cloud for hydrogen fusion to start making helium. And that's what we call the main sequence. The main sequence is this trail of stars running from top left to bottom right, and the sun is sitting here roughly in the middle of the main sequence. If the sun was a greater mass, it would be a little bit further up here, a little bit bluer. And if the sun was a lower mass, it'll be a little bit further down and a little bit redder, a little bit cooler. As I said, I think it is generally accepted that the sun was made from a hydrogen cloud and had lots of siblings, so it was probably made with hundreds if not thousands of other stars, but over time that cluster has drifted apart and we're now left with a star which is no longer part of a star cluster. And it's essentially impossible to tell which particular star cluster we might have originally come from. It looks like stars are born with planetary systems or protoplanetary systems, a lot of gas and dust surrounding the star, which will eventually become a planetary system. So as the hydrogen cloud collapses, the center gets hot enough to form a star, and what's left over beyond the star, many, many millions of miles beyond the outer limits of the star, there's gas and dust, which it looks like are likely to become planetary systems. Until a few decades ago, we didn't know how many stars had planetary systems. It now looks like it is very common. Radio telescopes are now looking at lots of stars in the early stages of formation, and we've seen many, many examples of protoplanetary disks around star systems which are not yet forming the planets that we would recognize today. These protoplanetary disks are relatively cool compared to the hot star in the middle, and so they are generally imaged using radio telescopes rather than optical telescopes. Radio telescopes such as this one looking at wavelengths that are millimeters in size rather than wavelengths that are microns in size, which would be the case for optical telescopes. This particular telescope array is in the Atacama Desert in South America. We can think about how planets will grow from this disk of matter, this disk of gas and dust. And just as I said that galaxies grow by accretion, it looks like planets grow by accretion as well, from small objects up to larger and larger and larger objects. The smallest objects are nanometers in size, not much bigger than molecules, and eventually they'll grow into objects that are megameters or gigameters in size. So dust will eventually coalesce into grains, which might be microns in size. You can see these grains aren't very smooth, they aren't very regular. They're the result of lots of tiny grains of dust coming together to form grains that are many microns in size. And those grains will eventually coalesce into pebbles, and those pebbles will eventually, under gravity, start to form planetesimals, in other words, small planet-like bodies, which eventually will grow until we find objects that we start to recognize as planets, which will start to hoover up larger and larger particles in the disk of the surrounding the star. It would be useful to know roughly what timescale this occurs on, this accretion from tiny grains of dust up to planets. And we're not absolutely sure, but we think it goes on this sort of timescale. Planetesimals will form over millions of years, and they will grow into planets over tens or hundreds of millions of years. If we think about the sizes of the Earth and the size of Jupiter and just place them on this scale here, Earth being somewhere between 1,000 kilometers and 10,000 kilometers, and Jupiter being rather larger than that, well, that naive picture would imply that the small planets are built first and then they grow until they become large planets like Jupiter or Saturn. And it would imply that Jupiter and Saturn were the last of the planets to form. But we don't think that's what actually happened. When we do simulations, when we run simulations, we find that far from being the last planet to form, we think Jupiter was actually the first planet to form. So how can something so large grow so fast? And to understand that, we need to understand this concept of the frost line or the ice line, sometimes called the snow line. If we think about the radiation from the sun, things will be kept fairly warm up to the point at which things like water and methane and ammonia will freeze. In other words, when we calculate what was going on in the early part of our solar system, we calculate that at distances greater than 5 astronomical units, 1 astronomical unit is the distance from the Earth to the Sun. Bear in mind these distances are by no means to scale. Beyond a distance of 5 astronomical units, we're far enough away from the Sun that it's cold enough for water and methane and ammonia to actually stay as solid ices. Any closer to the Sun than about 5 AU, these will evaporate and we will only have gases and perhaps some of the heavier elements that I mentioned in the last talk that are part of the recycling of what happened in previous star generations. So, close to the Sun we have gases, but at a greater distance from the Sun we have ices, and that is what makes the difference. So if we think about how quickly the Earth grows, where it's in an environment of essentially gas, as opposed to how quickly Jupiter grows, when it's in an environment of essentially ices, that explains the difference. If we look at the growth in size on the vertical scale as a function of time on the horizontal scale, we think the Earth might have grown something like this. Less material to accrete, and so it grows relatively slowly. But for an object like Jupiter, once it reaches a particular size and a particular mass, then it can hoover up a lot of these ices that exist beyond the frost line, and so Jupiter and Saturn will grow very quickly. And it's that difference, are you inside or outside the frost line, that dictates the difference between the ice giants and the gas giants, Uranus, Neptune, Jupiter and Saturn, compared to the rocky planets which are close to the Sun. So we think the timeline looks a little bit like this. We think the ice giants Uranus, Neptune, Saturn and Jupiter grew in these very early stages. Jupiter probably started to grow first, and then Saturn, and then the ice giants. And by about 10 million years, they had effectively grown to their full size. And only afterwards do the rocky planets start to accrete enough material, remember not ices, just the various bits of gas that are around, and start to produce the rocky planets. They're picking up not only gas, but they're also picking up a little bit of the heavier elements that were made by previous generations of stars. I think it's interesting to note that Jupiter, Saturn and the ice giants actually formed before fusion kicked in. In other words, our Sun wasn't actually generating power, wasn't actually generating energy from fusion until after Jupiter, Saturn and the ice giants were made. So in a sense, Jupiter was born before the Sun, which is an interesting way of looking at it. Rocky planets then came along. I've noted right at the bottom here Theia. Theia is simply a hypothetical object which we think hit the Earth in the very early part of its development, and that caused a disruption which ultimately gave rise to the Moon. In other words, it shattered the Earth and produced a whole load of spallation material which ultimately condensed into the Moon that we see today. We think that happened 4.5 billion years ago. In terms of the growth of planets, well, we have a number of questions yet to be answered. Where did Earth's water come from? If there were no ices to be hoovered up in the region inside the frost line, how come we have oceans? What caused the late heavy bombardment? I'll explain what that is in just a moment. It's an early bombardment that we think occurred in the early solar system. Why is Mars so small compared to Earth? Barely 10% of the Earth's mass. Why aren't the inner planets all similar in size, in much the same way that Venus is a similar size to the Earth? And how did other structures in the solar system come to be? The Kuiper belt is a belt of icy objects sitting outside the orbit of Neptune. And the Oort cloud is a hypothetical cloud which is a huge sphere, maybe a fraction of a light year in diameter, that we think is surrounding the solar system because we believe that is where comets come from. That's the only explanation as to why we get comets coming in from a great distance. We must have a large number of icy bodies a great distance out. And yet the protoplanetary disk doesn't seem to be the explanation for the Kuiper belt or the Oort cloud. So something must have made them in the first place. We have clues from looking at what's going on our moon. We can see impact craters on the moon, and they were made at different times. And when we look at the Mare Imbrium, that's the one in this circle there, that flooded with lava, and there don't seem to be many craters inside that particular lava plain, implying that if the Mare Imbrium was made 4 billion years ago or so, which is what we believe, there haven't been many impacts since then compared to what happened before that. Rock samples from the Apollo missions indicate that a heavy bombardment took place about 4 billion years ago. And that's what we call the late heavy bombardment. So any hypothesis we have about how the solar system came to be has to also explain why there were so many rocks flying around in the solar system 4 billion years ago to produce the cratering that we see on the moon and also on planets such as Mercury. So we come back to our picture and our timeline of what we think happened. So we've got some explaining to do. And there are two hypotheses that explain what happened in the early solar system that disrupted what otherwise would have been a very peaceful situation. A change of the orbits of Jupiter and Saturn, which is called the Grand Tack, and later on, many millions of years later, the so-called Nice model, based on the University of Nice. It is not the NICE model. So let's first look at what is believed to have happened with the orbits of Jupiter and Saturn that explain some of the formation of the solar system, the so-called Grand Tack. So what happened before the Grand Tack is we think we had a solar system that looked like this: Jupiter, Saturn, Uranus and Neptune in orbits which all look fairly sensible. And remember the frost line. So what's going on inside the frost line is we have lots of small chunks of rock called planetesimals with essentially no water because it's too warm there for water to exist. Whereas outside the frost line, shown here in blue, we have lots of planetesimals with some water. So the color coding is just so we can keep track of where the water is. So what is thought to happen is, according to this animation, Jupiter orbit shrank, and it shrank to the point where it started to bulldoze its way through all of this water containing material and then expanded again. Now, I'm not going to go into the details of exactly why we think this happened. It's to do with the gravitational influence of a planet moving in a solar system where there's lots of objects. These planetesimals had a non-trivial mass in total, and as well as the planet pulling on these planetesimals, then the opposite is true. These planetesimals will also be pulling on Jupiter and Saturn. So what happened in this mid-tack? The tack refers to the fact that the planet orbits seem to shrink and then expand again, much like a boat will tack into or out of the wind. So at one point it is thought that the orbits of Jupiter and Saturn were much closer to the Sun because of this tack and this shrinking of orbits because of the interaction between these planets and everything else in the disk around the Sun. In the process, as they shrank, they would be scattering all sorts of these chunks of rock into different parts of the solar system and, as it happens, into the asteroid belt as well. After the tack had finished, we now find Jupiter and Saturn are not so far away from where we find them today. Uranus and Neptune are now much further out than they were. But the important observation is that a lot of the material that used to be roughly where the Mars orbit is now, a lot of that material has been depleted by Jupiter effectively bulldozing its way into the inner solar system. And that meant once the rocky planets started to form, Mars had very little material from which to actually accrete its structure compared to Earth and Venus. And that is why Mars is so much smaller than Earth, simply because Jupiter had hoovered up so much of the material and scattered other material to different parts of the solar system, depriving Mars from growing any larger. The other major disruption, which is assumed to have taken place in the solar system, occurs with the so-called Nice model, based on the University of Nice coming up with some simulations to explain what might have happened not a few million years, but many hundreds of millions of years after the solar system formed. So this is now after not only the formation of Jupiter and Saturn and those changes to orbits, but after the formation of the rocky planets. And we're now only looking at what's going on in the outer solar system. The rocky planets have formed and are relatively unchanged by what we're showing in this simulation. So now we have Jupiter, Saturn, Uranus and Neptune according to this color coding. So we're now looking at a scale not just a few astronomical units, we're looking at many tens of astronomical units. And we believe at this stage the Jupiter, Saturn, Uranus and Neptune would have been surrounded by a disk of icy objects, but only extending up to a distance of some 30 astronomical units or so. And the simulation tells us that not much happened for quite a few million years until the orbits of Saturn and Jupiter became resonant. And that means that a particular period of Jupiter happened to be a multiple or a submultiple of the orbit of Saturn. In other words, it took Jupiter, say, 10 years to go round the Sun, and it took Saturn 30 years to go round the Sun. So Jupiter would do 3 orbits in the same time that Saturn took to do 1 orbit. When you get this so-called resonance, that can have a major disruption to the orbits themselves. So we start with a large dense disk of small ice and rock planetesimals, and then we're going to see what happens over the next few 100 million years. To start with, not much. But then when Jupiter and Saturn happen to hit resonance and their orbital periods coincide, there's a sudden rearrangement of orbits. Notice Uranus and Neptune suddenly increase their orbits significantly, and in the process a lot of these icy bodies have been scattered, some of which have been scattered into the outer solar system, forming the Kuiper belt and probably the Oort cloud. But as well, a lot of these particles, a lot of these rocks have been scattered to the inner solar system, and that is why we had the late heavy bombardment. A lot of these icy particles rained down on the Earth and effectively brought water to the Earth on a time period of hundreds of millions of years after the solar system began. And that is why we have oceans now, because of this rearrangement in the outer part of the solar system. So the planetesimals that were in a relatively concentrated disk have now been scattered to the inner solar system, the late heavy bombardment, or ejected into the Kuiper belt and ultimately into the Oort cloud. This is only a hypothesis. It's very difficult to prove this is actually what happened, but these simulations seem to indicate that this is a plausible explanation for why we have a solar system with the planets where they are, with an asteroid belt, with a Kuiper belt, with an Oort cloud, as well as why the Earth has oceans and why Mars is relatively small. So it's a complicated story. It is by no means a simple linear argument from we started with this and we ended up with that. We have to take into account what was going on with the star itself, when fusion occurred, when the gas and the dust were available to make planets. We have to think about the frost line, what's happening to ices outside this distance and the gases inside this distance. And we need a couple of hypothetical rearrangements of the solar system, the grand tack in which Jupiter and Saturn change their orbits, and then the Nice model in which Uranus and Neptune change their orbits, and possibly even interchanged. The ordering of Uranus and Neptune might well have swapped over. And we need all of those elements to explain the complexity of the solar system. So the take-home message is the solar system is not a clockwork orrery. It's not a clockwork system in any sense of the word. The solar system is actually chaotic. It might seem nice and serene now because nothing much seems to be changing other than the orbits are the planets are orbiting around the sun according to calculations, and we seem to be able to predict where they're going to be thousands of years into the future with no problem whatsoever, or indeed thousands of years in the past. But we think it had a very chaotic origin, and although it seems stable now, things could indeed be very different millions of years into the future. If you go far enough into the future, we don't even know how many planets there will be in the solar system. Maybe Jupiter will decide to throw out some of the smaller objects in the solar system if it decides to change its orbit again. Watch this space. Thank you.